So this is essentially an extension of the barium 137M video, because after experimenting, cleaning up is part of the process. This video follows the experimental tutorial on determining the half-life of barium 137M. Somehow the sunlight was hitting at a weird angle, which is why the footage looks a bit strange. I'm sorry for that. Here I used a tissue to avoid discarding the entire cardboard underneath. The experiment involved cesium-137, which is an important detail because we sort our waste by radionuclide. Some labs sort waste by type of radiation and half-life instead. We do it just by radionuclides. This is what the workstation looks like after an experiment. Chaotic. During cleanup, two people are involved. One holds the detector while the other one actually cleans up. The beaker was used to precipitate barium 137M from cesium-137. However, after rinsing as a part of the experiment, the detector shows no remaining activity, which is in this case sufficient to be considered clean. The filter attachment of the Buchner funnel also came onto contact with radioactive material, so it also has to be measured as well. No activity is detected, meaning it can be cleansed thoroughly with cleaned molecule water. Here's the leftover water from the first attempt. It's definitely still radioactive. When in doubt, always consult the supervising assistant. Conveniently, all the liquid waste fits into a Falcon tube. For the lab course, we usually provide a large container where you can drain your waste into. There is no detectable activity in the vacuum flask anymore. Investigating residual activity. There still seems to be some residual activity on the workstation. Could it be from the stand? Yes, the platform shows activity, but strangely, so does the surface underneath. So what now? Wipe the area with acetone and then check for the activity transfer to the tissue. Unfortunately, it didn't. Typically, this is done multiple times in hopes that the activity on the equipment decreases while it increases on the cleaning wipes. If this doesn't work, as in this case, the stand can of course still be used, but you have to place a sticker with a warning, caution, active but still usable on top of it. There still seems to be some activity on the workstation, which is unacceptable. Using the contamination monitor, we slowly scan the surface to pinpoint the contaminated area. Once located, the contaminated paper is removed. A larger section around the active area is always cut out. Here there is a jump in the footage because my professor pointed out a mistake in the video. Now you see a scene showing a proper lab cleaning day. We follow the same procedure as described before. In this instance, we dealt with uranium contamination. Wearing gloves, I marked the contaminated area, measured it again, and disposed of it. Disposal costs depend on volume, but we do not have the equipment to compress or incinerate the waste. Underneath the paper, there is a layer of saran wrap, and below that, there is the final steel plate. The saran wrap acts as an extra barrier to protect the table from acid drops, while the paper, which is disposable, has now done its job. Cleaning the surface is very straightforward. Remove the old paper, put a fresh layer on top, voila, it's all clean and you have a usable workspace again. Occasionally we patch up the paper, but during regular lab cleanups it's completely replaced. In some nuclear labs, active experiments are conducted in trays to contain the radioactivity to a designated area. This is ideal but often impractical for us due to space constraints. Compressing or incinerating paper waste would be worthwhile, but we lack the facilities for that. Even though most of our radioactive waste is combustible, it's handled by the Regional Waste Collection Facility, which has an appropriate infrastructure. We are a relatively small lab and produce minimal waste. For example, a container of sodium-22 and cesium-137 waste costs a few €100 for disposal, but it isn't collected annually. In fact, it includes waste generated from research and 2 semesters worth of lab courses. What happens to the low-level waste in Germany, that's beyond our responsibility and will get its extra video. I hope this video provides some insight into how I clean up after experiments, and since I've received some questions about it quite often. A special thanks goes to the Working Group of Analytics and Fundamental Nuclear Chemistry from Dr. Eric Strupp and the Division of Nuclear Chemistry at the University of Cologne, and to my Patreons. With that being said, thank you for your attention and goodbye.